Okay, I'll चेंज ये 1 घंटे का है ना, सोना तो बीच में
अभी से चलने में ना इसे रख दे फिर डाल दे
बीच में तो
डिस्टर्ब होंगे, बीच में करेंगे।
इसको ये रख दे, इसको सोने के नीचे कम कर दे।
Okay, so are there any other questions? So then, if there are no questions, let me start. So one question was about so the last class we did this problem of heat transfer in a rectangular slab. So we had discretized this into 2 elements, and the node numbering was like this. So global node numbering 1, 2, I think I had said this 3, this has 4, and the element numbers were this has 1, this has 2, and coordinate system was having origin here. So the question was, see when, and there was a heat flux input here, and this I think I had said 2 bars per meter. So the question was, I think one of the question was why I didn't consider the contribution to the boundary integral for this particular edge. So actually, if you look at, when you are looking at the first element, that is what I had mentioned, that contribution from 1 and 2, when you sum them together, that would actually get cancelled out. So if you look at just this integral, contour integral for the first element, which is here what you have is H transpose Qn into ds. I'm not putting the minus sign before, I'm just talking about this. If you remember, F internal for the element we had said as minus of this, so that's what exactly it was. And this is the contour integration along the entire boundary of element number 1. So actually what you can do is this contour integration means you can say the integration along edge 1 to 2, so I am just not putting the limits but just saying that 1 to 2, and then you have H transpose Qn ds, then plus this integration can be written from this is local node number 3 for the element, so I am using still the local numbers for the first element. So this is then 2 to 3, and then you have of course the same quantity H transpose Qn ds, and the last term is then this again 3 to 1, so you have integration from 3 to 1 H transpose Qn ds, right. So this is what actually you will have, this as the cyclic integral along the boundary. So along this boundary plus this boundary plus this boundary for the first element. Now out of this, of course, we know that along this boundary there is no heat flux input or output, so this term is actually 0. And for this we know Qn is given as minus 2 watts per meter. So and then the integration ds you can write as dy, and the limits of integration 0 to 2. So we had evaluated this actually. And the last one is this. When you look at the last one, you are going from this point to this point, that is 3 to 1. So but only problem with this is that this Qn is an unknown. So actually if you look at what we are doing is, if you separate out the first element, What we are doing here is, of course, here whatever is given externally, that we are considering, and here it is 0, and well, let us say that no, on this edge Qn is positive, that is it is along the outward normal. So for the first element, and again it won't, in general it won't be uniform, no, this would also be variable, although I have drawn these almost the same height of arrows here, but this in general is going to be an unknown quantity, because we do not know there, because this is the heat exchange between element 1 and element 2 at this common boundary. So we are assuming it to be some unknown quantity, but only thing what we can say is that since we are ultimately going from edge 3 to 1, so along this edge, when you go from here to here, the shape function L2 is going to be actually 0. So only shape functions which would be non-zero is L1 and L3 for this element, first element L1, then L2 is corresponding to this, L3 is corresponding to this. So only non-zero components are this separately we evaluated. If you look at this term, in this term specifically, if you look at, of course, the along this edge x and y, both of them are going to change. ds you can write square root of dx square plus dy square, and you write the equation of this line, you can write y in dy in terms of dx and so on. So the integration then can be expressed in terms of either dx or dy, and then you put the limit from here to here. So you will do that, but finally you will see that when you are doing that integration, you will have L1 non-zero, L2 would be 0, and L3 would be non-zero, and this Qn ds. I am just talking about only this term, and this is unknown, but anyway whatever is this function into L1 will give you some integrated value. This L1 into Q1 integration from this point to this point will give you some value, and similarly this integration of L3 Q1 ds will also give you some value, right? So then this is about the contribution of this from the first element. When you look at the second element, element number 2, now for the element number 2, this contour integration is f internal. Again now what we can do is locally we said that this is say node number 1 and this is node number 2, this is node number 3, local number. So if I write for the second element, this is local node number 1, local node number 2, this is local node number 3. And the integration when you do, so the cyclic integration now would be this is from 1 to 3, that is 1 to 2 here, you are going now for the second element, and for the second element if you also look at the actually from the boundaries whatever the heat transfer is taking place. So one is that this edge you are maintaining at a certain temperature, so depending on of course finally the solution. So let me for the time being say that there is some heat output here, but that this is actually an unknown, and let me say that this is some Qn dash, which is again a function of it is going to vary along this edge, because here you are prescribing a temperature, finally we know that. So wherever you are prescribing a temperature, there will be again some flux, but this edge whatever heat flux is coming from this side is actually going to enter here. So although you will have the same variation whatever you have here, so this is the scenario here you have here, and here Qn is 0, but this is just no entering, but the magnitude is same Qn whatever you have here, and let us say I have said that this is Qn dash. So now if you evaluate for the second case, so you go from this point to this point, which is locally 1 to 2, so this is integration minus of course you have here, then 1 to 2, and then you have H transpose Qn ds, but this Qn is actually minus, so let me put this as minus here. Why minus? Because the same Qn here I have taken as positive. So if the heat is going from this element to this element, so from this element it is heat flux is away from the outward normal, so it's positive. For this element heat is actually in the negative direction of outward normal, that is entering in the element, so it's negative, but the quantity is going to be same whatever you have for the first element, because this is the common boundary. So you have this term as minus H transpose minus Qn ds, and the integration is of course from 1 to 2, so you, that limit and all you have to take care, and then the next part is integration from 2 to 3, and there the Qn is actually 0, so integration from 2 to 3 H transpose into Qn ds, and this is actually 0 because for that edge heat flux is actually 0, and then the last boundary is we are doing the integration from 3 to 1, and then you have this H transpose into Qn dash ds. This is what you'll get. Now this is already 0, and we have again in this also, this is actually an unknown quantity, so we cannot exactly evaluate this integral, but only we can say that which out of this is finally H transpose is going to be 3 by 1 vector, so which of those elements are going to be non-zero, that is what you can say. So now if I look at again going from here to here, then this shape function along this boundary is going to be 0. So you will find that in this particular term only first and third would be non-zero, and first and second would be non-zero, third would be 0, because you are locally for this local node number 1, this is local node number 2, this is local node number 3. You are going from 1 to 2. So along this edge 3 is going to be 0. But in terms of global, this is corresponding to the same node number what we had here, and this one is corresponding to the same node number what we have here. So you will find what I was saying, that when you are doing the assembly, so actually this contribution and this contribution from here, when you add them, they will cancel out each other. This is coming from the first element, this is coming from the second element along the same boundary, that is same edge, common edge shared by the two elements, that is actually this edge. So this gets cancelled out, so that is why we had not considered this. So finally this is 0, this will finally get cancelled out, this and these two would cancel out. So we did not consider that. Of course this was evaluated because we knew this Qn along that edge, and this is what finally in the assembly I had said, that when you look at this H transpose Qn dash, and this integral is actually evaluated along this boundary. So along this boundary you will find that L2 is going to be 0, so it will give contribution corresponding to this node and only this node. So there we had said some Q1 and Q2. So the logic behind taking that two unknown heat sources, I know this global node number 3 and global node number 1 was based on this argument that along all the common boundaries, from one element the heat is, if it is leaving out, other element it is going to enter. So finally those integrals, when they are assembled together, they would cancel out. So we do not actually bother about evaluating these integrals along the internal bound edges, common edges shared by the elements. We only look at wherever this is known, so we take into account that, and wherever the external boundary conditions are there, we will have to take into account that. So if you recall what I had done, so let me go back to that. And I'll again explain you there because I don't want to write it. So finally what I had said was that in the assembled system, we had added one term here. If you recall, you can see your notes, one term this, one term here. And these are the nodes where temperature is prescribed. So for here onwards, we will not be like, of course, 1D it is straightforward. We can visualize from on one element how the forces, internal force would be coming onto the other element and vice versa. So we were properly accounting for that. Here, there would be so many edges and accounting for all of that. Ultimately, they are going to get cancelled out, so it's not actually necessary. But we must understand that when we are writing the element level governing equations, actually those terms are there. But finally, when you after in the assembled system, if you see leave as it is like this, so then you would find if I don't many books you find that this kind of reactions are reaction fluxes, or in case of mechanics problems reaction forces and moments are not taken into account. Then what you find is see T1 and in this case 1 and this T4 they were already prescribed. So only unknowns are T2 and T3. There are 4 equations. So only 2 unknowns and 4 equations. So it's actually inconsistent system. So number of equations and unknowns must be same, and those are nothing but wherever the primary variables are prescribed, there would be corresponding unknown secondary variable. So that is now this is in terms of nodes. So these are the point heat sources. So T1 and T3 they are prescribed. So you have to add corresponding unknown reaction flux here like Q1 and Q3. So this is always, so that now if you look at the T1 and T4 are known, T2, T3 are unknown, Q1 and Q3 are unknown. So you have 4 unknowns and 4 equations. So the system is consistent. So that's basically the purpose of bringing that out. So okay. So is there any other question? So let us know the last class I mentioned that then we will take the 4-noded quadrilateral rectangular element formulated in physical coordinate space. But I think before that I want you to attempt a problem. So let us say now if we take a solid mechanics problem, a plane stress or a plane strain problem, how you will formulate it 3-noded triangular element level governing equations. So let us take next is the plane stress. First I want you to try, then I of course I'll explain. Plane stress or plane strain problem of basically solid mechanics. So what here we mean by this is that now you have some domain, it can be actually a regular domain or it can be irregular domain, and you will have some boundary condition and loading, but the loads are in plane. So if I call, let's say here this as my x direction and this as y direction, so the loading in this may be external, body forces, they are only in plane, so having x and y components, and there can be boundary tractions also. So this is a general situation what we are talking about, and if the thickness is very small, we can approximate this problem as plane stress, and if the thickness is very large, we approximate it as plane strain problem. So if it is thin sheet like this, so even this is a problem like that. So this is screen under the weight of this rod is subjected to a vertically downward force, which is force acting in the plane containing the significant dimensions, that is the width here and the height, but the thickness is very small. So if you look at the normal stress in the thickness direction, that would be negligible actually, 0. So we take this problem as a plane stress problem. But on the other hand, if it is let us say that let's say a situation like this, where the forces are acting, this is the thickness direction, the forces are only acting say in this direction or in this direction. This dimension is very large, so predominantly you can say that the strain in this direction is 0, and you can treat this problem as a so you just model only one cross section, you will consider the forces here, forces here, forces here, and associated boundary condition, and in this direction you take as the plane strain condition. There are many such examples one can give. So now you want to develop the element level governing equations for this, considering a triangular element. So 3-noded triangular element. So now you, for this problem, you want to formulate a 3-noded triangular element, and for the element, say this is x, this is y, and again we are talking of 3-noded triangular elements. So these are local nodes 1, 2 and 3, and the corresponding coordinates are going to be x1, y1, x2, y2, and x3, y3. See, this is now a mechanics problem, and we are also since the loads are only in the plane, so the middle surface is not going to move in the z direction. So we will have only two non-zero displacements, and those displacements are basically displacements along x and y direction. So let us say the displacement in this direction is u, and the displacement in this direction is v. U and v, they are going to be functions of x and y. That means some point which is originally here moves by a distance u along x direction and a distance v along the y direction, and u and v are functions of x and y. So how will you go about formulating the element level governing equations for this? Right? Is the question clear? So first element level governing equation, of course, then the discretization of the whole domain into certain number of elements, assembly of the element level governing equation, imposition of boundary condition solution, and post processing. So those steps remain same. What changes is basically the element level governing equation. So if you look at here, the first basic starting quantity is displacements, which are two displacement u along x, which is a function of x and y, v along y, which is a function of x and y. we are assuming that they are independent of the thickness coordinate. Then strains, you talk of strains here, so you will have epsilon xx, which is del u by del x, and of course u and v are assumed to be unknown functions of x and y, so we will leave it this as it is. Epsilon yy is the rate of change of v along y, and then you also have in plane shear strain, which is del u by del y plus del v by del x. So this is as far as the strains are concerned. Now depending on whether it's a plane stress or a plane strain problem, epsilon zz may be 0 or non-zero depending on the problem. Of course gamma xz and gamma yz, they are all going to be 0. So gamma xz and gamma yz, they will always be 0, because z and x or z and y are always going to remain perpendicular. That is the deformation mode we are assuming here, and epsilon zz could be 0 or non-zero depending on plane stress or plane strain, but that will not be a separate independent quantity. And then when you talk of stresses, right, so again you would have stress sigma xx, sigma yy, shear stress tau xy. For both plane stress and plane strain, these would be non-zero, but for depending on whether the problem is plane stress, then sigma zz would be 0, epsilon zz non-zero. If the problem is plane strain, then sigma zz would be actually non-zero, because you are not allowing it to deform, so obviously there has to be a corresponding constraining force, which is sigma zz, and then the epsilon zz would actually be 0 in that case. So depending on this, you have then the constitutive relation, that is stress strain relation. And I am going to assume again here that the material is linear, elastic and isotropic. So for this case, what is the relationship between stress and strain? So if you consider plane stress case, for plane stress condition, what is the relationship between stresses and strains? I don't know. No. So if you don't know, let me give a yes. I think some of you would know definitely, because you would have done the same thing in continuum mechanics. But let me briefly summarize that. So easiest thing to do is express actually first strains in terms of stresses, and then depending on plane stress or plane strain, you can actually write finally what we want here, because now we are looking at formulating the problem in terms of displacements. So we want to express everything in towards the displacement. So we want to write stresses in terms of strains and strains are in terms of displacements. So but it is easier to write strains in terms of stresses, so let me start with that. So if you want to write say epsilon xx would be, so if you have a problem where there is some sigma xx, sigma yy at some point within the body, actually is a point, and you also have say this shear stress here. So this is like along x direction sigma xx, this is sigma yy, and this is tau xy, and of course in the perpendicular direction you have sigma zz are 0 or non-zero. So epsilon xx would be is the normal strain along x direction. So one direct component is sigma xx upon E. Then when you are trying to elongate in this direction, this is what is the contribution. But when you are having a normal stress in y direction also, that will have tendency to contract the dimension along x direction. So you have that term contributing to minus Poisson's ratio nu times sigma yy by E. Then if you also have, let us say, the stress along the thickness direction, so that will also try to reduce the dimension along x. So minus nu times sigma zz upon E. So this is actually normal strain epsilon xx in terms of sigma xx, sigma yy and sigma zz. So similarly you can write, and it's an isotropic material, so no coupling between the normal strains and shear stresses. So these are the only contribution. So similarly sigma yy would be directly because of the sigma yy, you will have sigma yy by E as your epsilon yy, that is this stress sigma yy is trying to elongate this dimension, but then sigma xx would try to contract this. So minus nu times sigma xx upon E minus nu times sigma zz upon E, similarly due to z. So if I have say positive stress in this direction, this tries to elongate this side, but it is will try to contract this and this because of Poisson's effect. So also if I have a stress in this direction, it will try to elongate this but try to contract these two dimensions. So that is why this minus sign. That's how physically you can think of this. Of course it has a mathematical derivation behind it. And so similarly, if you want to write epsilon zz, that is going to be sigma zz upon E minus nu times sigma xx upon E minus nu times sigma yy upon E, where E is Young's modulus and this nu is Poisson's ratio. We used it earlier. So in this we have this is a general relationship for relationship between normal strains and normal stresses for linear elastic isotropic material. What we want is, here what we have is strain in terms of stresses, finally we want stresses in terms of strains. So now for the plane stress case, see when you look at the plane stress condition, then sigma zz is 0. Now for the plane stress case means sigma zz is equal to 0. So if you put sigma zz 0, that is this term is 0, this term is 0, and this term would be 0. So then you will find that epsilon zz is just expressed in terms of sigma xx and sigma yy, and now using these two equations, this and this, I can express sigma xx and sigma yy in terms of epsilon xx and epsilon yy. So if you use these two equations, this is just a brief whatever you would have learned. I am briefly summarizing the constitutive relation for the plane stress condition. So what you can do is, now using these two equations, this equation and this equation, express sigma xx and sigma yy in terms of epsilon xx and epsilon yy. So you find that when you solve sigma xx and sigma yy from these two equations, what you would get is, so that I want to write in the matrix form, so sigma xx sigma yy, and I will also bring in tau xy and I will explain you how I am writing that. So this is, you would see that this relationship is now, see for one dimensional case, Hooke's law simply sigma xx is times epsilon xx, but now this constitutive relation in between is going to be a matrix. So here what you have is epsilon xx, epsilon yy and gamma xy. And when you solve for sigma xx and sigma yy from these two equations, that relationship comes in this form. You can cross check it, 1 minus nu square, 1 nu and 0. Of course sigma xx is expressed only in terms of epsilon xx, epsilon yy. It is independent of gamma xy, no coupling between normal stresses and shear strains for isotropic materials. Similarly this will be nu 1 and 0, and then the tau xy is g times gamma xy, and for isotropic material g is E upon 2 into 1 plus nu. So that relationship is also, I am putting it here. So since you have E upon 1 minus nu square already there, so you want it as minus 1 minus nu by 2. So when you multiply E upon 1 minus nu square with 1 minus nu by 2, you will actually get E upon 2 into 1 plus nu. So that is your G. So this is the situation. Now you can call this, in the vector form we are writing the stress. So I can call this as just a sigma vector, and this is constitutive matrix. So let me call that as C, and then this is the strain, which is, let us say, epsilon. So I am denoting this as sigma, this as C, and this as epsilon. So this C is referred to as constitutive matrix, relationship between stress and strain, constitutive matrix. Because it is depending on the material properties, which depends on the constitution of the material, what are the constituents of the material, and that is why this is named as constitutive matrix. This is for the plane stress case. Now if you talk of plane strain, so in case of plane strain condition, what you have is actually epsilon zz 0. If you take epsilon zz equal to 0, then what you need is, then sigma zz would not be 0. So then what you do from the third equation, where you have epsilon zz is equal to sigma zz upon E minus nu upon E times sigma xx plus sigma yy. So since epsilon zz is 0, you can say sigma zz is going to be nu times sigma xx plus sigma yy. In case of plane strain case, epsilon zz is 0, sigma zz is non-zero, but sigma zz is not independent. It is written in terms of sigma xx and sigma yy. Then what you actually do is put this sigma zz in the first two equations here. I will come back here. So in these two equations, whatever I have written for epsilon xx and epsilon yy, now you substitute your sigma zz as nu times sigma xx plus sigma yy. So then the first equation would become epsilon xx is equal to sigma xx upon E minus nu times sigma yy upon E, and then you have minus nu times sigma zz, which is minus nu square upon E into, you will have sigma xx plus sigma yy, isn't it? Sigma zz is nu times sigma xx plus sigma yy, and epsilon yy is equal to sigma yy upon E minus nu times sigma xx upon E, and minus nu upon E times sigma zz. Sigma z is subsequently this, so this becomes sigma xx plus sigma yy. And again, now I can express using these two equations, sigma xx and sigma yy, in terms of epsilon xx and epsilon yy, right? So this is just the summary of what we do in basic solid mechanics course. So now if you invert this relationship, you can finally write putting all together, including this shear stress sigma xx sigma yy and tau xy, again in the form of a constitutive matrix and the strain matrix here. So you have this side again epsilon xx, epsilon yy and gamma xy, and the form of the constitutive matrix comes out as E upon 1 minus I think I need little more space, so let me call this as C and I will separately define that. So this is C in between, and that C I am going to define. So here this C comes out as, you can solve that, these two equations, and get the form of C. So this comes as E upon 1 minus I think no, you have to solve this. So can you solve and tell me what is this relationship? E upon 1 minus 2, no, I think yeah, 1 minus nu and 1 minus 2 nu, 1 plus 2 nu, no. Just solve these two equations. Can you do that? These two equations solve for sigma xx and sigma yy quickly. It's not a difficult thing, you just combine some of the terms. Yeah, both you have. Yeah, so, yeah, if you solve, I think. So, what I'll do is you actually get this. It is nothing but solving these two equations for sigma xx and sigma yy. So, you'll have to first club right hand side sigma xx term together, sigma yy terms together, and then solve those two equations. You can express sigma xx, sigma yy and tau xy in terms of constitutive matrix into this. So for the plane strain, this matrix will be different from the whatever C matrix we have for the plane stress case. But the form is going to be same. In both cases, we have three independent components of stresses and strains. So this you solve, maybe I think it's a straightforward process, so you should be able to do that. So you complete this, okay. No, next time I will also let you know. This solution is straightforward. So once you have done this, now here onwards there are two ways. Either we develop the first governing differential equations, then the weak form or integral functional or weak form to be used for the element level governing equations, or you can also, because it's a mechanics problem, linear problem, we can write the total potential energy functional also directly. So let me write that. So if you write the total potential energy functional, I think this is here 1 minus nu into 1 plus 2 nu, 1 plus nu into 1 minus 2 nu. So it should be something like this C matrix is E upon 1 minus 2 nu into 1 plus nu, and then you have here 1 minus nu and the corresponding term. So I think I'll work out and then rather than wasting time in that. So total potential energy functional, if I want to write, let us say I. So this will consist of what all? Total potential energy functional in a solid mechanics problem? Strain energy. So strain energy is going to be half then integration over volume and sigma xx epsilon xx plus sigma yy into epsilon yy plus tau xy into gamma xy. These are the three terms. So other pairs, no sigma zz or epsilon zz, one of them is always 0 for plane stress and plane strain. So what you will have is simply sigma xx into epsilon xx plus sigma yy into epsilon yy plus tau xy into gamma xy and the integration over volume. So this is 1, right? Then potential energy of external forces acting on the body. So now we are trying to write this for an element. So this integration is over volume of an element, and then as I said, there could be body forces. There is force per unit volume along x direction, force per unit volume along y direction. So corresponding to those, the potential would be obviously work done is positive, potential is negative. So integration over volume, let us say force per unit volume along x direction is FBx. So this would be FBx plus u into FBy into v dv. So this is the potential d capital V. I think I am using capital V for the volume, not a small v. So d capital V. So this is the potential of body forces. That means within the body we have force along x direction, we have force along y direction per unit volume. So Fbx into dV will give you total force, into u will give you work done, and then minus times of that will give you potential energy. This we did for 1D problems as well. So the same concept. And then when you are considering an element, so there would be traction forces also. So as I said, no, this is 1, 2 and 3. So on each boundary there would be some traction force. Traction force I can write on each of these boundaries in terms of the traction force component along x direction. So let us say Tnx and Tny. These are the force per unit the area of the the boundary, this boundary. So essentially area means this length into thickness, because when you have a number of elements, one element is going to exert force onto the other element, and that force we are representing in terms of force per unit area along x and y direction. And assuming that these are no positive forces, although they can be positive and negative in actual situations, so minus, and then this is going to be obviously boundary integral, because now we are going along the boundaries of the element, so over the entire boundary, and then you have Tnx into u plus Tny into v, and then let me put this as ds, but I am saying Tnx and Tny are the force per unit areas. So area means this length and into thickness. So let me put the thickness here separately, if h is the thickness. So this includes all the distributed forces, of course, over volume and over lines. Of course, you can also have concentrated forces, so that I am not considering here. So we can actually rewrite this. This is the total potential energy functional, consisting of strain energy, potential of the body forces, and potential of boundary forces. These are the three different contributions to the total potential energy functional. What we can do is write this I know in terms of matrix vector products. So the first term actually you can write, again the volume integral we can split into, because we are assuming that nothing changes along the thickness direction. So volume integral can be written as h dx dy. So then this integral would be written as integration over area of the triangle, and this I can write actually as sigma xx, sigma yy, tau xy transpose into epsilon xx, epsilon yy, and gamma xy, and this is h into dx dy. This volume I am writing dv as h into dx dy. H is the thickness of the perpendicular to xy. So this is the first part, and the second also I can write again this volume integral. I can say that as integration over area, and then I can say that these two I can put as a u and v transpose into, you have fbx body forces, fby, and here you have h dx dy. dv, that is differential volume, is written as thickness times dx dy. So you take a small area here, this area, this is dx, this is dy, into h gives you the volume, differential volume. And the last term is minus integration over the entire boundary of the element. And similarly this term also you can write in the same form, ub tnx tny, and then you have of course ds. So h I have written here, so wherever you want to write h, you can write here h ds. You get the same, whatever we have written here, you are going to get the same thing. Now when you open this and multiply the vectors, you are going to get the same quantities. You can further rewrite, as you see the first term, I is equal to half of integration over area, and then this is sigma. Sigma can be written as C into epsilon. So I can write this term as actually epsilon transpose into C transpose, but C is symmetric, so its transpose is same as C, and then you have that term as epsilon, this one h into dx dy. That is this vector I am writing as no epsilon vector here. So you have finally, of course the other two terms remain same. Know that integration over area of the element, uv transpose into fbx fby h dx dy, and plus this is its cyclic integral again u and v transpose into traction forces tnx tny and ds. So this is what you have as your integral functional. In this integral functional, if you look at, when you look at the definition of strain, highest order derivative of both the variables u and v is only first derivative. And this problem, because highest order derivative in the integral functional is actually 1, so the variables themselves would only be the primary variables. So that is, in this case the primary variables are going to be only u and v. More rigorous way of looking at that is of course through the differential equations, and then getting the weak form and arriving at primary and secondary variables. But in this case we can also identify by looking at our functional, also energy functional, that highest order derivatives are u and v. In this case it is straightforward. So highest order derivative of u and v is first derivative, so 1 less than that is basically here you have only the variables themselves, u and v as the primary variables. So now once you have this basic background in mind, either the differential equations or the understanding of this plane stress plane strain problem, so what are the unknowns, the displacements, the strains, the stresses, and then the constitutive relation either for the plane stress case or for the plane strain case, and then the total potential energy functional. So the basic background is now known. But C is symmetric, so C transpose is same as C. You are right that this is actually epsilon transpose into C transpose, but C is symmetric, so therefore C transpose is equal to C. C is going to be symmetric in both the cases, plane stress as well as plane strain. This of course for linear elastic problems it is always symmetric. So that is why I have written it like this. Now, so what is the next step to develop the element level governing equations? Now the same whatever methodology we have learned for the heat conduction problem, same thing you can use here. So now the next is approximation of the field variables, in this case u and v, within the element. So if you are considering as I said, triangular element, 3-noded triangular element 1, 2 and 3, and with somewhere global coordinate axes and x and y here. So again we see highest order derivative of the variables in integral functional is only first derivative. So what we need is whatever solution we assume, at least it should be differentiable once with respect to x as well as y. So then that means what? I can have u as a0 plus a1x plus a2y. This is the minimum required because I can now differentiate and get a non-zero value of del u by del x, also del u by del y. So similarly v we can assume as b0 plus b1x plus b2y. So in case of heat conduction problem we had only one variable, that is temperature. In this case we have two variables, that is the only difference, rest of the things remain same. And since I said no, we want here the continuity of u and v across the elements, so we need to have u and v as the degrees of freedom at the nodes. So here I must have u1 v1 as the values of u and v at node 1, and similarly u2 v2 as the values of u and v at node 2, and similarly u3 v3. So overall for at each node we have 2 degrees of freedom, displacements along x and y directions. For the element we have 6 degrees of freedom. Elemental degrees of freedom are 6, consisting of u1 v1, u2 v2 and u3 v3. So then what next we need to do is again the way we did for the heat conduction problem, and see again if you look at u is defined by 3 constants a0, a1 and a2. Corresponding to this there are 3 values of u within the nodes of the element, which is your u1, u2 and u3. So we can express a0, a1, a2 in terms of uniquely in terms of u1, u2, u3. Similarly b0, b1, b2 are coming in defining v, that is transverse displacement along displacement along y direction. So we see that corresponding to v we have v1, v2, v3, again 3 degrees of freedom within the element, and these 3 constants b0, b1, b2 can be easily expressed, uniquely expressed in terms of v1, v2 and v3. So if you follow the same procedure which we did for the temperature, because the steps are same except that now you have 2 variables u and v, you would see that you can again write u and v put together in terms of interpolation function, same area coordinates. Now I am not repeating the same step. u1 is equal to a0 plus a1 x1 plus a2 y1, and u2 is equal to a0 plus a1 x2 plus a2 y2 and so on. So 3 equations and then solve for a0 and a2, put back here and collect the coefficients of u1, u2, u3, get the shape functions. Those shape function here also would be those area coordinates L1, L2, L3. But then what we want to do is we want to write this in such a way that we put all the elemental degrees of freedom into one vector, and typically the procedure is that first we write the all degrees of freedom, although one can actually change, but all the degrees of freedom in this elemental vector corresponding to first node, then second node and third node. So I will do here u1 v1 first. One can also do first u1 u2 u3 v1 v2 v3, that way also one can formulate, but here typically the practice is that we first put all the degrees of freedom of first node, then second node of the element, and then the third node, or depending on the number of nodes. So u2 v2 u3 and v3. So this is your vector of elemental degrees of freedom, which is 6 by 1 vector consisting of u1 v1, u2 v2, u3 v3. Then here u is defined by u1 u2 u3. So the shape functions would be L1 0, L2 0 and then L3 0. That means you are just saying like T we had temperature finally, T as L1 T1 plus L2 T2 plus L3 T3. Same way here you are saying U is U1 L1 plus U2 L2 plus U3 L3. Then here you will have 0 L1 0 L2 0 and L3. This you call as your interpolation matrix, H into that as DE. So this is your H and this is your DE. So this is one. Then you need, because now we are going to substitute this, L1, L2, L3 same definitions, there is no change in that. The next is we want to substitute this approximation in the integral functional. So I also need the expressions for strains. So I can write epsilon, and epsilon is either plane stress or plane strain. Both cases we have epsilon xx, epsilon yy, and gamma xy only as the independent quantities. So these can be written as, this is del u by del x, that you know. So we will have a matrix here and the vector of elemental degrees of freedom, which is u1 v1 u2 v2. So you will find that most these things are actually same type. The method is not changing, only the problem is changing. So epsilon xx is del u by del x. Del u by del x then would be, here you will have del L1 by del x 0, del L2 by del x, then again 0, del L3 by del x, and then 0. So essentially when you multiply this first row here with the this vector, you get epsilon xx, which is del u by del x, is equal to del L1 by del x into u1 plus del L2 by del x into u2 plus del L3 by del x into u3 here. So that's the same expression. Same way you can write for this. So this is 0 here, del L1 by del y 0, del L2 by del y 0, and del L3 by del y last. And then epsilon x gamma xy is del u by del y plus del v by del x. So both the terms are there. So here you will have derivative of u with respect to y. So that is del L1 by del y into u1 plus you will have del L1 by del x into v1 plus del L2 by del y into u2 plus del L2 by del x into v2 plus del L3 by del y into u3 plus del L3 by del x into v3. So this is what is your no, and you will find again similar to what we did for the no temperature heat conduction problem. This matrix is actually going to be constant, and this you call as B, and this you call as your DE. So this is your B, and this is your DE. We have already defined. And again, no, you can write L1, L2, L3 area coordinates. You can write their derivatives. So in terms of difference of x and y coordinates, the way we did for the temperature problem. So these derivatives are same. Only thing they are used differently. So now next step is developing the element level governing equation is straightforward, right? So everybody can do that, right? Now you can get what form of your element level stiffness matrix is going to be, what form of your load vector due to external plus internal, everything you can write exactly. So you just have to substitute now all of this into this integral functional, and then the solution of original differential equation or equilibrium of the problem is equivalent to saying that delta I equal to 0 for arbitrary delta DE, and you will get your element level governing equations, which would be of the same form, that is KE. I am not repeating those steps. KED is equal to F external for the element and plus F internal for the element. For now your KE is now going to be integration over area of the element, and into you have here B transpose, in between now you have constitutive matrix C into B and H into dx dy. So this is going to be your element level stiffness matrix. And if it is a plane stress problem, then this C is different. If it is plane strain problem, C is different. Otherwise nothing changes. So the form remains same, and your F external is going to be, this we are taking from the only basically body forces. So the integration over area of the element into H transpose into, you will have FBx, FBy and H into dx dy. So that you can see is coming from the second potential energy term. And then F internal is only the boundary forces acting on the elements, which is integration only over the closed contour, I mean the boundary of the element, and this also would be H transpose into T and X, T and Y, H into ds. So this is, you see that this form is always straightforward always, okay. So once you understand the problem, either the differential equation or the integral functional, you can decide what kind of element shape you want to choose, what is the approximation you want to choose, and then you can develop the element level governing equation in this fashion. So I know you can, similar to what we did a heat transfer problem, you can also take a simpler problem and try to actually solve a simple problem using this three-noded triangular element. And typically this element in solid mechanics, three-noded triangular element is also known as constant strain triangle. Why constant strain? Because within the element the strains are going to be constant, because displacements u and v are linear in x and y. So when you differentiate, like del u by del x is going to be constant within the element, del v by del y is going to be constant within the element. So these strains are going to be constant within the element, and therefore the name of this triangle is constant strain triangle, CST element. So in solid mechanics we call it as CST, constant strain triangle. Of course in the heat conduction problem also temperature gradients are also constant, so you can call that as a constant temperature gradient element for heat conduction problem. This is known as constant strain triangle. So as a home assignment, I'll give you a problem, a couple of problems. So the heat transfer problem also, what you can do is whatever problem we did in the last class, suppose rather than discretizing only into 2 elements, if you discretize into 4 elements, say like this, rest of the problem so you can try to solve the same heat conduction problem by discretizing into 4 elements like this. Now you can number the nodes, global node numbering, say you can say 1, 2, this has say 3, this is 4, this is 5. Element numbers you can say this is 1, this is 2, this is 3, this is 4. So you need to write xy coordinates. The dimensions and other data are same. So you try to solve this problem with discretization of the same problem into 4 triangular elements. This is one for the heat transfer. And the another problem you can try solving is, let us say if I have a plate, again similar kind of a situation, and this end of the plate is fixed. It's a mechanical problem, and you have distributed force here. This is force per unit length, let me say, and maybe part of this there is a force here. Let me put over the full boundary. The dimensions maybe you can take same. I think this 2 meter, and this also say you can take as 2 meter, or 1 meter also you can take. Take the steel properties, so Young's modulus is you can take 200 GPa, and nu as Poisson's ratio as 0.3. This force you can take as 2 Newton say per meter, or 20 Newton per meter. That means it's only per unit length. Thickness is already multiplied here, and let us say this side, this force is 10 Newton per meter. Thickness h is you can say take 2 mm. Then discretize into 2 or 4 triangular elements and try to solve, assemble the system level element level equations into global system, impose the boundary condition and try to solve this. This is your homework problem. Okay. So with this I stop here and we'll continue in the next class. If you have any doubts or questions, you can ask outside.